Okay, thank you first of all for coming. Today I will describe for you a little bit of dynamics on networks. And the second part I will concentrate on representation of networks for data, and I will do something similar to what I already said during the seminar, the workshop we had 1 week ago. I want to speak to you about dynamics. So now the network is nodes, and each node in general is a dynamical system. How many of you knows what is a dynamical system? You know, of course, but so a dynamical system is a system which is having some dynamics. That's why it's called a dynamical system. And I want to speak about to you about the problem of synchronization. If you remember, yesterday I have shown some experiment with metronomes, and in fact synchronization, that is the setting of collective phenomena, is very, very old. You see, the first person who discovered it is Christian Huygens in the 17th century. And the legend says that he was sick. He was sick and standing on the bed, and he observed two pendula which were hanging at the same beam. And exactly like the metronome, this pendula interchanges some forces because they interacted. They had some dynamics, the pendula, and he observed that no matter which were the initial condition of the pendula, at a given time the pendula started to operate in sympathy. He called this sympathy, not synchronization. That is in this way, in antiphase. Okay? And he understood very well that the reason for this sympathy or synchronization today had to be attributed to the forces that this pendula interchanged because of the fact that they were hanging at the same beam. So if they did not work like this, they were dephased and the beam was slightly oscillating, so it transmitted forces from one to another. In modern time, we study synchronization on dynamical systems. So I want to make you an example which is very famous, and then we pass immediately to another example. This is the Kuramoto phase oscillator. So imagine that you consider many of such pendula, but they are not pendula, they are oscillators. Okay, they make like this, not like this. And to be very, very simple, imagine that each oscillator can be associated to a phase, this phase, theta, okay? And this phase, theta, so each oscillator you can see like a point in the unit circle, has an equation which is the simplest equation you can imagine, that is the derivative in time of this theta, or this phase, is the frequency. Okay? So if you integrate this equation, you have that time t, the phase of the nth oscillator is omega t. Okay? So these are points which are rotating or counter-rotating in this unit circle depending on the sign of this omega. And you can take many, like in the experiment there were 64 metronomes. Imagine that you are now considering 1 million of these oscillators. And then you have to find a way to couple them. And the idea is that you couple by means each oscillator, you see, oscillator n has a derivative of the phase equal to the frequency plus a coupling term, which is the sum over all the oscillators of the sinus of the phase difference. So I look your phase, I look my phase, I compare the two phases, I put sinus function, and this is the force that I interchange with you. And now I show you a movie because I want to show and explain to you what we are speaking about. You take many of these, and you see initially they have different frequencies and different phase, so they are distributed around the unit circle, but then in time they synchronize. All these oscillators acquire a unique phase, a unique frequency. You see? They have a unique phase and they move together with the same frequency. Understand? So we are describing this kind of phenomenon, which is called today synchronization, and we want to study this phenomenon on networks. Okay? So I have now a network. Therefore, the connections between the dynamical system are not like here all to all. There will be some matrix, which is the matrix, the adjacency matrix of the network, which tells me which oscillator, which system is connected with each other, and I want to describe this phenomenon, synchronization. So the first class today will be dedicated to probably the most important and most elegant result in synchronization, which is called the master stability function. Okay? The master stability function. So let me write the problem in a very general form. Instead of having one phase, I imagine that the state of a given oscillator or given system is a vector x, I. Okay? The phase is just a phase, but I can have an oscillator which has phase and amplitude, or even 3 variables, or 4 variables, or 5 variables, or in general d variables. So the state of a node is a given vector, and we suppose that this vector belongs to a given space Rm. So M are the variables that define a dynamical system. Okay? Then I put here the derivative in time, so I put here dot. Dot means derivative in time of this vector. And I say this vector evolve as a function f of xi. This function is a function from Rm to Rm, okay? And it tells me how, in the absence of the network, my dynamical system would evolve alone, like derivative of the phase equal the frequency, is the same. Notice that this function can be whatever, okay? But we are making already an assumption, and the assumption is that my dynamical systems are identical, because my function here is constant. It does not have the index I. So I have a bunch of dynamical systems, and all of them are identical. Okay? Of course, this is an hypothesis we have to make to get important results, and then you will see that the results are also valid for slightly non-identical systems, but for the time being they are identical. So I have these systems. I, it's a number that goes from 1 to n, and n is 1 million. Big, huge number of these systems. And now I have to specify the coupling, and I, in a very general way, say I have a network, so these are nodes. I put here plus. I put here sum over j equal 1n Aij, so the adjacency matrix of the network, okay? And I imagine that this dynamical system speaks to each other by means of an output function, h. So I have another function h, which goes from Rm to Rm, and this is h xj minus h xi. And this sigma. Let me explain, therefore, what is written there. Here you have dynamical systems which are identical and which are ruled in the absence of the network by the function f. H is an output function. It tells me how they are coupled. For example, H can be linear, so this is the difference between the two vectors, but it can be quadratic, it can be whatever. For example, in the case of the Kuramoto oscillator, it's a sinus of, you know? A is the adjacency matrix of the network, and sigma is the coupling strength. So how much is the strength of the coupling in each one of the link of the network? So for the time being, I am making the following assumption. Systems are identical. They are identically coupled in the sense that also the function h does not depend on I. So different nodes are coupled in the same way in the network. And I am assuming that the network is bidirectional, so unweighted and undirected. So the matrix Aij is symmetric for the time being. Then I will show you that this is much more general. But for you to understand the way it works, this is the situation. Okay? So I have a very huge system. Imagine this is the brain. This function f is describing single neuron. These are how the neurons are coupled among them. Okay? And I have millions of these systems. Okay. First of all, I can rewrite this equation in the following way. Fxi plus sigma sum j1n of Laplacian ij hxj. Because if you remember, the Laplacian is the matrix that I obtain from the adjacency, in which instead of having 0 in the diagonal element, I have minus the degree of the node. And this is exactly what I have, because you see this depends on I and not on j. So I have minus each xi how many times? As many ones I have in the row. So I have minus ki hxi, and here I have the elements of the j different than I matrix. It's clear? Okay, so I want to study now this equation. X dot equal to this. And I want to see if I can say something rigorously about synchronization. Okay, first important property. Yesterday, if you remember, I told you that the Laplacian L is a matrix which is 0 row sum. So it means that if I take one row of the matrix, and I sum all the elements, I obtain 0. Okay? This is extremely important because it guarantees us that the synchronous solution, which is x1 equal to x2 equal to x3 equal to xn equal to xs synchronous, this solution exists and is invariant with respect to sigma. What I mean exists. If you plug this solution here, you have xs dot equal fxs, which is a single dynamical system, and this is 0, because all xj are equal, and the Laplacian, when you sum the row, is 0. And it's 0 for all values of sigma. So the fact that the Laplacian is 0 row sum is ensuring me that the synchronous solution exists for all possible value of the coupling strength. And it's the same. It's invariant. So I can study the stability of this solution. Not only I want the solution to exist, but I want the solution to be stable. Because if it exists and it's stable, I then observe it. I have a chance of observing it. So the solution exists, and now I put this solution in red here. The solution is the solution of the following equation, xs equal to fxs. Notice that this equation is how much dimensional? Which is the dimensionality of this equation? M. So I don't have to now take 3 million m, but I have only m. This is an m-dimensional equation, which defines the solution of the state, the synchronous solution of the state, of the network. And now I want to study the stability. And how I study the stability? Very simple. I define vectors delta xi, which are xi minus xs. These vectors tells me how much I am deviating from the solution. How much node I is different from the synchronous solution. I plug this solution, this delta here in the equation, and I take the linear part. I linearize the equation. Okay? I get, believe me, delta xi derivative equal to Jacobian of the function f. You know what is a Jacobian? Calculated in xs, in the solution, okay, times delta xi. And this is this first part. Correct? Then I have a second part, which is plus sigma sum j1n Laplacian ej Jacobian h xs delta xj. Okay? I made nothing but the linearization of this equation around the solution x equal to xs. What I want is that all this delta xi goes to 0. No? if all my delta xi's goes to 0, it means my solution xs is stable. Now I'm using, for the first time, the property of the Laplacians. Laplacian is a zero-row sum, but it's also a symmetric matrix. So the Laplacian is diagonalizable. Not only is diagonalizable, but it contains a set of eigenvalues which are real numbers and a set of eigenvectors which form a basis of Rn. You know these things, no? Okay, so point number 1, the Laplacian is zero-row sum. If it is zero-row sum, please believe me, there is a theorem that tells that the first eigenvalue, lambda 1, is 0. So lambda 1 is 0. Lambda 2, smaller or equal than lambda 3, smaller or equal than lambda 4, smaller or equal than lambda n are instead positive eigenvalues. And the eigenvector v1 corresponding to lambda 1, I write it here, is 1 over square root of n 1, 1, 1, 1, 1, 1, 1. Because the Laplacian is zero-row sum, the first eigenvalue is 0, and the eigenvector that corresponds to that eigenvalue is the eigenvector which has equal components, 1, 1, 1, 1, 1, 1, 1. So you understand that this eigenvector here is the synchronization solution. Because I have a very big phase space, dimension n times m, many, many dimensions, but this solution is the diagonal. x1 equal x2 equals x3 equals x4 equals x5. So this solution is exactly the solution where this eigenvector is lying. Correct? No? And therefore, since the set of eigenvector is a basis, the transverse space, all direction perpendicular to this manifold, to this diagonal, hyperdiagonal, is nothing but a superposition of all the other eigenvectors. So all the other eigenvector furnishes a basis of all the space perpendicular to this direction. Correct? So what I have to do, I have to ensure that in all these directions, my diagonal is attracting. So an error that I make here goes to 0, is damped. Or if you want, the associated Lyapunov exponent to all the eigenvectors that corresponds to all the eigenvalue different than 0 is negative. I have a linear equation, so a linear equation has two solutions. Or 0 if the coefficient is negative, or infinite if the coefficient is positive. In one case, I'm unstable. In one case, I'm stable. Okay, so now I need to make some trick. Because I want to reduce these things. I want to discuss and have a very, very big and important result. So what I do is I introduce big delta x. And big delta x is a big vector in this space, which is delta x1, delta x2, delta xn. Okay? This big delta x tells me how all the network is distant from the synchronous solution, because it contains information of all the nodes. I can write equation for this big delta x. Take this equation, sum up, and I get delta x big dot equal to jf xs direct product with identity delta x plus sigma j1n Laplacian direct product with jh xs delta x. I did only one thing. I just summed up all these equations. These equations are n equations. Okay? But now I know that the eigenvectors of my Laplacian is giving me a basis. So my big delta x, which is a vector here, can be written as a linear combination of my eigenvectors. No? So my big delta x can be written as sum k1n eta k vk. Vk are the eigenvectors of the Laplacian matrix. Eta k is a vector in Rm. Okay? Correct? And now, I plug this inside this. I make scalar product, mixed scalar product with all possible vectors so that I isolate each k and write equation for eta k. I write equation for this, which is the projection of my error on each one of the eigendirections of my Laplacians. Correct? So, if you took note, I write for you the equation of eta k, which are the following. Eta k dot is a vector eta k, equal to jf xs mass sigma lambda k jh xs eta k. I just used the fact that when I plug here the eigenvectors, this matrix is applied to the eigenvector is the eigenvalue times the matrix. Correct? That's the property of eigenvalue, eigenvectors. And then I made, now you have a beautiful, fantastic equation. Why it is beautiful? Why it is fantastic? Because now look at this equation and compare this equation for the eigenvector k with this equation for the eigenvector k prime. Two different eigenvectors. The only difference is this. The only thing that depends on k is lambda k. You see? Jacobian the function f calculated in the solution. The other is Jacobian the function h calculated in the solution. And the only thing that depends on the direction, on the specific k, is sigma times lambda. And now I make the following trick. I define a parameter nu equal to sigma times lambda. And I study the following parametric linear equation eta dot jf(xs) mass nu jh(xs) eta. This is a linear parametric equation. Which is the dimension of this equation? M. So I reduced 1 million nonlinear equations in one single equation, which is giving me the solution XS, and one single linear parametric equation. For each value of nu, it gives me if the corresponding eta is negative or positive. The coefficient is negative or positive. Okay? So what I do, I plug everything in a CPU, and in 10 seconds, 1 second, it gives me immediately for whatever h and whatever f, the solution, which is the sign of the coefficient here, which is in other terms called the maximum Lyapunov exponent, as a function of nu. So I have the maximum Lyapunov exponent as a function of nu. Okay? Correct? For each value of nu, I take this axis, I divide this axis in 2,000 different points, and I calculate my function. It's called the master stability function. Why? Because now all possible networks is a collection of points here. It's a set of eigenvalue, which I multiply by sigma, and I obtain a set of points here. So to study the stability of a system, I just need to write this function and then read the value of the function at the location of the eigenvalues of my Laplacian. You see how beautiful is this? I separated dynamics from structure. Structure is nothing but a series of points here. The dynamics is what is giving me the master stability function. Now, one eigenvalue is always 0. We saw the first eigenvalue is always 0. When you multiply 0 for sigma, you have always 0. And this is the maximum Lyapunov exponent of the single system inside this diagonal, which, if the system is chaotic, is positive. And now, this is the very, very important result. If I am interested in studying synchronization at low values of sigma, when I have little coupling, the first synchronization phenomenon, I can have only 3 cases. A monotonically increasing function, f and h. Notice that this depends only on f and h. So you give me the system, f, and you give me the way the system speaks between them, h. Immediately I calculate the master stability function, which is a function valid for whatever network. So the function can be either, say, with no crossing with nu, or with 1 crossing, or with 2 crossing. So I call it class 1 systems, class 2 systems, and class 3 systems. What happens if I have a system in class 1? You give me the system, you give me the h, I calculate, and I see it is class 1.
So it is chaotic everywhere?
No. Chaotic is chaotic always, because chaotic is inside. I conclude immediately, finish of my problem. No network can synchronize your system.
This is what I mean by chaotic.
Because whatever network you will have a distribution of point here, and your function will be always positive. So if you have a system in class 1, you already say, I cannot synchronize this system, never. This is unsynchronizable. Okay? Now, class 1. Class 2. You have a system in class 2, so you give me h, you give me f, you give me h, and I calculate the master. I repeat 1 second of CPU, and I get nu star, this intersection. What I can say? I can say the system is synchronizable always. Why? Because whatever network you prepare, it is sufficient that sigma times lambda 2 is larger than nu star. So your first eigenvalue, non-zero eigenvalue, is at the right of this, and all the other eigenvalues will be at the right of this. Look at the eigenvalues. Lambda 2 is the smallest. So if I put the smallest times sigma, because this is sigma lambda, to the right of this point, automatically all the others will be to the right of this point. So all the direction of the space will be contracting, will correspond to negative values. So I have an analytic definition of the threshold to synchronization. The threshold to synchronization is written here. Sigma larger than nu star divided by lambda 2. I tell you, you have to increase your coupling strength up to the threshold for synchronization, which is nu star divided by lambda 2. So the threshold of synchronization, if you want, in class 2 systems is completely determined by the second largest eigenvalue of the Laplacian matrix. If you want to synchronize with less sigma, you have to increase lambda 2. If you give me another network with a larger lambda 2, you need less sigma to synchronize. Clear? Okay? So you have, this is beautiful, you see, it's really fantastic, because you you give me whatever system you want, whatever coupling function you want, and I immediately tell you what you can do in synchronization. What happens in class 3? class 3, you have two intersections. You have nu1 and nu2. Okay? And now, in order to be synchronous, your spectrum of eigenvalues of the Laplacian multiplied by the same sigma should stay here. No, because it's the region where the function is negative. So, the condition now is, you have two conditions. One condition is that sigma times lambda 2 must be larger than nu1. So the smallest should be at the right of this. But at the same time, for the same sigma, sigma lambda n, the largest, should be smaller than u2. And now in class 3, therefore, if I have a system in class 3, there are networks that structure that synchronize this system and structure that don't synchronize this system. Because it depends on the spectrum. If I have a very wide spectrum, it may be that when sigma lambda 2 is here, sigma lambda n is already out of here. So this network is not good, because I'm always unstable in a direction or in another direction of the phase space. I will never see synchronization. Correct? So, in class 3, you can speak about synchronizability of a network. So the capacity of this network to give rise to synchronization. And you understand very well that, for example, the most important, the most easy way is when this network, when this spectrum is as much as degenerate as possible. Because if all these eigenvalues are equal, okay, then when sigma 2 is inside, also sigma n is inside. You are guaranteed. In general, synchronizability for a network in class 3 is lambda n divided lambda 2, which is by definition larger or equal than 1, should be as close as possible to 1. So you need a spectrum which is very not wide, the opposite of wide, thin. So this is the mass stability function, and you understand that it's very good because this is a very, very generic result. You give me whatever dynamical system, whatever function of coupling, and this tells you the property of synchronization of the network. I just want to show you one possible application that people did of this. Of course, this is the demonstration, the simplest demonstration for symmetric matrices and whatever. Then people started to extend the validity of the mass stability function to non-symmetric matrices, non-identical systems, blah, 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 blah. But I want to show you a very nice, for example, and simple application of this. I'm now asking you, if I am in class 3, please give me the optimally synchronizable graph. I give you a system, and you design the way of coupling the system so that, okay, the network is maximally synchronizable. And the issue is this. You have to make a degenerate spectrum. So what to do? You take your nodes, Suppose this is the network. You now start labeling your nodes with numbers. For example, this node 1. Then you take the neighborhood of node 1, these 2, and you call 2 and 3. Then you take the neighborhood of 2 and 3, which is this plus this, and you go 4, 5, and 6. So all the time you start from one node, neighborhood of the node you label, second neighbor you label, third neighbor you label. When you arrive to the diameter, you already put a number to each node. And now you choose the directions on each link, which are from the oldest node to the newest. So this is like this. This is like this. 2 to 3 is like this. 2 to 4 is like this. 4 to 3 is like this. 3 to 6 is like this. And 3 to 5 is like this. So you construct a directed network. And now you put on each node a weight which is the 1 over the in degree of the receiving node. For example, in this link, the receiving node is 2, which is the in degree of node 2, 1, because it's only received by node 1. So in this link, my weight is 1. 2 to 3. 3 receive from 1 and from 2. So I here put 1/2, 1/2. Because the in degree of 2 is, of node 3 is 2. Node 4, the in degree is 2, so 1/2, 1/2. Node 6, the in degree is 1. Node 5, mean degree is 1. And now let me write explicitly the Laplacian of this network. The Laplacian of this network is a 6 times 6 matrix. First row, 0, 0, 0, 0, 0, 0, because node 1 is not receiving from anything. Node 2 is only receiving from node 1. So I have 1, minus 1, 0, 0, 0, 0. Correct? Node 2, node 3 is receiving from node 1 and from node 2. So 1/2, 1/2, minus 1, 0, 0, 0. Node 4 is receiving from node 2 and node 3. So 0, 1/2 from node 2, 1/2 from node 3, minus 1, 0, 0. Node 5 is only receiving from node 3, so no node 1, no node 2, 1 node 3, node 4, minus 1, 0. Node 6 is receiving from node 3, so again 0, 0, 1, 0, 0, minus 1. This is the Laplacian. Now, can you tell me the eigenvalues of this Laplacian? 1 is 0. And all the others. This is a triangular matrix. All the others are 1. So this is a way to make a network maximally synchronizable. You give me a network, and what I put is directions in the link and weights of the links, so that this network is the one who maximally synchronizes any dynamical system. So if you are interested in synchronization, you know an application of this. Very simple application. Because no one other network can do better than having a Laplacian which is completely degenerate. Except lambda 1 equal to 0.
So basically any acyclic network
Sorry?
So the only property we need here is the cyclicity. So we do not have
This is not always like this because, again, this is for a network which is originally symmetric. If the network is originally asymmetric, then in general, what you have to do, the requirement is that it is still diagonalizable, but in general, the eigenvalues are complex numbers. They are not real numbers. And therefore, you don't have a function lambda of nu, but you have a function lambda of real part of nu and imaginary part of nu. So you can have escape from the imaginary part. So it's a little bit more complicated. Okay, so this is probably the most important result in synchronization, I repeat, because it allows you to assess when a network is synchronizable, when a network is not. And it's 1:35, so I will make a little bit of pause here, and then the next hour I will speak a little bit about networks and data, repeating something that I already explained during the workshop and putting more details on this one. Do you have questions on this one, on networks and dynamics? Did you understand everything? It's not so easy. It's a little bit difficult, but it's really, really elegant. It's really, really nice. Okay.